In this little exercise I'm going to have a quick look at exploratory factor analysis. The data set I have here is from a little study we did, and it measures a range of things, but I'm particularly interested in whether or not a new scale we've developed, which is a measure of adolescent depression, hangs together in the way it was designed to. So what I'm interested in is whether or not the instrument has construct validity. One of the ways that we typically assess whether or not an instrument's got construct validity is to look at how it was theoretically designed, what factors it was theoretically designed to measure, and see how that stands up with regard to real data collected from real participants. So the first step in doing this is you collect the data. In this case we should have something like a 4-factor solution for this particular data set. We would expect 4 different sorts of concepts to come out of the solution based on previous theory. Now to check that that's true, I'm going to go to Analyze, Dimension Reduction Factor. What factor analysis or exploratory factor analysis does is it takes a large set of items, typically making up a questionnaire, and it tries to reduce that to the smallest number of factors which adequately describes the domains of that instrument, or the latent structure of that instrument. So in this case I've already selected my items. Okay, I think what I'll do here is undo all of this so you can see how I did it in the first place. So here you can see on the left I've got my list of item names. I can turn off the item long labels here, and what we're going to look for is the TADs. Okay, so we grab TADs 1 through 20. So we have 20 items here which represent things like I try to follow the rules, I get into fights, I believe my life. They're indexes of adaptive or maladaptive behaviour, which might tell us something about how depressed an adolescent is. The first thing we want to do is find out if these things are correlated with each other in general, and therefore have some latent structure that allows them to be analysed. If we're correct, then what we should have is 4 subdomains, each with about 5 questions loading onto it. Each one of those blocks of 5 items measures some particular aspect of adolescent depression, such as their cognitions, their emotional state, the behaviour that they engage in. So what we're going to do here is go to descriptives. I turn on the initial solution because I want to see that. I want the correlation coefficients because I want to see in general what the level of correlation is between items. What we're looking for here is moderate correlations. So we want to see at least some factors being correlated moderately, let's say 0.3 and above, and we don't want any factors going much beyond 0.7, and if we see any factors that any items which are correlating above 0.7 into the 0.9s, then we've got concern that rather than having 2 separate items there to address some domain, we're actually just asking the same question twice or 3 times or whatever. So we want to have moderate levels of correlation. We look for the significance levels just as a way of testing that those correlations are meaningful. Personally I don't actually like that, and it adds clutter to the output table, so let's say we turn that off for the moment. Determinant is a metric of the pattern of underlying correlation between them. It's something that's required by matrix algebra to determine how to divide the values within the table. I'll turn that on just so I can look at it. The KMO is probably the eyeball test that we're most likely to use. It provides an overall summary of whether or not the data is factorable. It has some latent structure. Now, there's rules of thumb here. Values less than 0.5 suggest that there's not sufficient correlation within the data set for the sample size to factor it. From 0.5 to 0.7, the data set's probably factorable. Above 0.7, there's a high likelihood that the data set's factorable. 0.8 is good factorability. Above 0.8, you may have an issue with multicollinearity or something of that nature. The reproduced matrix, when factor analysis is conducted, first of all, factor analysis finds latent structure by deconstructing the correlation matrix and then reconstructing the correlation matrix. So if we ask for the reproduced, we see what the correlation matrix looks like after factor analysis is finished deconstructing it and reconstructing it. Ideally, it should be much the same as the initial set of coefficients. And that being the case, we can find out whether or not our factor analysis is interpretable by the degree of divergence between the reproduced matrix and the original matrix and the residuals, or the amount of error left over, which is the difference between those two matrices. If the residuals are high, then the solution is probably not very good. If the residuals are low, approaching zero, then the solution is very good. It's preserved most of the structure. So we're going to continue. From the extraction phase, at this point, we don't know what the solution is going to be. We have a theoretical belief that there's going to be 4 components, but we don't know for sure. So what we want to do is get exploratory factor analysis to tell us where it thinks the solution should be. There's 2 ways we can do this. First of them is called Kaiser's criterion, and Kaiser's criterion says you should continue extracting factors until one factor is about the equivalent of one perfect variable, and the metric for that is the eigenvalue. An eigenvalue of 1 indicates that you're measuring about one perfect variable. So if we have based on eigenvalues and an eigenvalue is greater than 1, the number of factors that we extract should stop where the factor eigenvalue is less than 1. The scree plot is called Cattell's criteria, and Cattell's criteria is a metric, a graphical way of evaluating the degree of new variance added by adding an additional factor. It comes from Cattell's interest in geography, and Cattell pointed out that if you were to plot the eigenvalues against the number of factors, what you got is a steeply descending curve that flattened out at the bottom, and it reminded him of an escarpment at the side of a cliff. And he pointed out that at the bottom of the cliff there's a lot of rubble, stuff which is uninterpretable because it could come from anywhere along the slope. The scree plot is an analogue of that cliff. At the point where you've got rapid descent of the line, I'll show you what I mean by that in a moment, you can see that there's still meaning to be gained from extracting more factors. When the slope of the plot becomes flat at the bottom, then you've got less meaningful information. Well, Cattell said what we should do is use that as a decision point to decide how many factors to extract. Right, so we've selected scree plot based on eigenvalues, numbers greater than 5, we don't. Numbers greater than 1, we don't need to change anything else. Go continue. We don't need to select anything else at the moment because we're just deciding if the data is factorable. Okay. So the first thing we do is we get our correlation matrix, and you can see here this is diagonal matrix. You can see 1, 1, 1. We only need to look at the bottom triangle here to determine what's going on in the matrix. What I'm looking for here is values that don't exceed 0.7 in general. So we've got 0.67 there, but most of these are moderate to low. Doesn't matter if we get the occasional 0 or very low values. If some factors are at right angles to each other, they're orthogonal, then we would expect them to have 0 loadings. Likewise, it doesn't matter which sign we've got, that indicates whether or not the question is positively or negatively worded to some extent. So just looking through this, it looks like the data set's reasonably factorable with not a lot of, not overly redundant wording of items in it. So this looks like it's factorable. I mentioned the Kaiser-Meyer-Olkin measure before. You can see the Kaiser-Meyer-Olkin measure here is 0.885, so that's very good for a sample of this size. So what we say is that it looks like we have a factorable data set. For the moment I'm just going to skip over the communalities and I'll come back to these in a minute. If we look here at the total variance explained, okay, these are our eigenvalues. Now, what an eigenvalue is, as I said before, each value of one eigenvalue is like the equivalent of one perfect question loading onto the factor. So factor 1, or label component 1 here, has the equivalent of about 5.9 good questions loading onto it. Factor 2 has about the equivalent of 4.2 good questions loading onto it. Factor 3 has the equivalent of 1.5 good questions loading onto it. And factor 4, 1.4 good questions loading onto it. As a consequence, what we have here is we have an indication that's worthwhile extracting these first 4 factors. They're going to tell us something about the data that's more than we would get from just one question alone. When we get down to factor 5, it's only the equivalent of about 80% of one item. So Kaiser's criterion tells us we should extract 4 factors for this, and as it happens, our theory, at least our design principles, said there should have been about 4 factors. So, and these 4 factors would account for about 65% of the variance, at least 66% of the variance, which is quite good. Typically, people will report solutions that account for as little as 40% of the variance. Okay. Below this part, Kaiser's criterion, you can see Cattell's scree plot. Usually, what we're hoping to see here is a smooth curve with a well-defined elbow that comes through here. And so this value, if this was going to be a nice theoretically tidy solution, would be down here. Okay. In real life, what happens is frequently you get these sort of less than perfectly smooth solutions. So looking at this, we can see there's steep descent here, steep descent here, steep descent here. Not much change there between factor 3 and factor 4, and then an elbow here. Okay, so what do we choose here? Well, according to Cattell, we should choose 1 point before the elbow of the curve. So 1 point before the elbow of the curve, I guess, is technically 4-factor solution as well. It looks like both of these are agreeing that a 4-factor solution might be the best solution here, although one might look at this and say the 3-factor solution is about as good as the 4-factor solution, so perhaps the 3-factor solution is all we need. Okay. So having decided that we should look, let's say, between 3 and 4 factors, we can then rerun the analysis and start extracting solutions. Okay. Just before we do that, let's see how well we've preserved the data. Okay. You can see here the reproduced correlation matrix. Now what we're looking for here is a match between this matrix and the initial correlations. And if you look at it, broad eyeball value, it looks like we're getting much the same values in much the same order. We're getting low correlations near 0, about where we're getting low correlations near 0. High values about where we're getting high values. And our diagonal is close to 1. Now, there's some variation there, but it's not a great deal. If we look at the residuals, this is the amount of unexplained variance left after building the reproduced matrix. You can see most of our residuals here are around 0. So that in fact we've done a pretty good job of preserving the latent structure of the solution. Okay? That means that we've got faith that we can probably factor analyze this data set.